Uh, okay, so we've seen two examples uh, of how to show when a limit doesn't exist. So now let's take a look at how to show that a limit does exist and determine the value. So first of all, the actual formal definition of a limit is shown here in definition 2.1. So it's typically called the epsilon delta definition of a limit because when it's written, it says we say that the value of a limit is equal to L if for every possible epsilon greater than 0, we're able to find some delta greater than 0 such that this inequality holds whenever we have this inequality with delta, right? So this limit, there's a lot to unpack in this limit, and it's quite difficult to use in trying to prove that limits exist. So for the purposes of this course, we're gonna avoid using the epsilon delta definition of a limit. So what we're gonna use instead is an analog of what's called the squeeze theorem from Calc 1. So basically the sort of the idea behind the squeeze theorem is you might have a somewhat complicated function that you're trying to determine the limit for. If you're able to sort of squeeze or bound it with a simpler function that you're able to calculate the limit directly for, indirectly for, then that will give you insight on what the limit of the more complicated function is going to be. So that's sort of the rough idea of the squeeze theorem. So for a function of two variables, it's presented here as theorem 2.1. So this is sort of the formal setup here, but just below that, I give an outline of basically how we can apply this theorem to determine various limits. So I list basically the 4 steps here, right? So the first step is to go back to what we did previously and calculate the limit for some of these paths first, right? Because again, just looking at a function, typically you don't really know whether it's going to be one where the limit exists or doesn't exist. So we try to calculate some paths to sort of give us some insight into the value of the limit, and if the limit is going to exist, all the paths should have the same value L. So we take that value L, and that value L is exactly this L that's used in theorem 2.1. So if we suspect that the limit is going to exist for whatever problem we're dealing with, again, the calculated L from step 1 is the L that we use in this theorem here. So we first write down this expression, this absolute value thing here, right? So absolute value of the function minus L. So just write it down, and we take a look at it. It's going to typically be somewhat complicated. So we try to come up with a simpler function. That's going to be this function g of xy that satisfies this inequality here. And what's going to happen is that the limit for this function is going to be easier to calculate, and it should be 0 so that we can actually apply this theorem properly, right? So this limit should be easier to calculate, and also the value should be equal to 0. And if we've done steps 1 through 4 so far properly, then finally we can conclude that the value of the original limit is equal to L. So that this is the basic outline for using theorem 2.1. Okay, so again, I mean, here the description here at first can seem somewhat complicated. So let's try to break it down for example 3 on the next page. So again, to start it off, we have to calculate this limit for some paths like we've done previously. So say we set y, so the limit is still going to 0, right? So my AB is just the origin. So we set y equals 0 as we did previously. What does this look like? X squared times 0 over x squared plus 0 squared. The variable is x, so the limit is for x. I simplify. So the numerator is 0. Denominator is just x squared. Right, x squared plus 0. And then 0 divided by anything is 0. So the limit of a constant is just that constant, which is equal to 0. Okay, so that's when y equals 0. So to save some time, I'm not going to do every single calculation, but you can imagine if I try x equals 0, so just imagining it, what does it look like? It'll be 0 on top, and then 0 plus y squared on the bottom. So overall, it will be 0 over y squared, and then 0 divided by anything will give you 0 again, right? So again, I'm skipping that calculation, but I've just quickly described it there. So that's also going to give you a value of 0. So now let's try to set y equals x. So it'll be the limit as x goes to 0. What do we have? X squared times x over x squared plus x squared. Now we simplify. So x squared times x is x cubed on top, and then x squared plus x squared is 2x squared on the bottom. So now I can cancel the x's. So this x squared cancels 2 of the x's on top. So that's just, I still have an x left over. So now what does it look like? It looks like x over 2. And so this is as simplified as I can get it. So now I can just calculate the limit by plugging the value in, right? So x equals 0. 0 divided by 2 is equal to 0. Okay, so for y equals x, I also get a value of 0. Okay, so again, I mean, as you were calculating these different paths, sometimes it can't. Sometimes again, it's not obvious at all whether we should think that the limit doesn't exist and continue trying, or we should think that the limit does exist and then go to this this procedure here. So let's take a look at this function again, right? So I mean, one of the key things that we've tried previously is to compare degrees, right? So when you have sort of a mismatch here, the limit is 0. Here, when the degrees match, then it gives you a different value, right? So in this situation, if you look at the original function, the degree on top, so when you have multiple variables, the degree, you have to add up the powers. So the degree is for a single term, right? So the powers for a single term make up the degree. So in this case, it's 2 plus 1, which is 3. So the degree on the numerator is 3, whereas the degree on the denominator is 2, right? So you do it one term at a time. So the degree of this term is 2. The degree of this term is also 2. So overall, the denominator has degree of 2. So in this case, the degree of the numerator is bigger than the degree in the denominator. So I'm not going to say this is always going to be the case, because I mean, in the examples we're looking at, they're somewhat simple, so that we don't have to do anything too complicated. I mean, it could possibly be there could possibly be a more complicated example where this doesn't apply, but in this situation, because the degree of the numerator is bigger than the degree of the denominator, we can suspect that the limit is going to be 0, right? Because roughly the idea is that because the top has a higher degree, it goes to 0 faster than the denominator. And so because the numerator is getting smaller at a faster rate than the denominator, is going to overall dominate the calculation of the limit. And so we expect that the limit is going to be equal to 0. Again, I'm sort of just giving rough ideas, because in these kinds of multivariable limits, I mean, there's no really single method that you can sort of apply to every situation. But in any case, let's say we expect that this value is going to the limit is going to exist, and is going to 0. So let's write it down. So suppose we expect the limit exists and L is equal to 0. Okay, so if we expect the limit exists, we should be able to carry out this procedure outlined for theorem 2.1. Okay, so that's the first two steps here, right? So we've calculated some of the paths, and we expect that L is equal to 0. So now we're on step 3. So we write down this expression here. So the absolute value of the function minus L. Right. So let's write this out. So what is my original function? So that's x squared times y all over x squared plus y squared. What is my L? Right, so I suspect that the value of the limit is going to be 0, so my L is 0. So I just plug it in, and then just subtracting by 0 doesn't do anything, so the whole thing is the absolute value of x squared over x squared plus y squared. Okay, so that's what we get. Okay, so how should we proceed from here, right? So we have to come up with a simpler function, g of xy. So how do we do that, right? So let's try to look at this expression here, right? So again, one of the key things that we've tried to do previously is somehow reach a point where we can cancel out the variables, right? So how can I reach a point where I can cancel the variables? So here, the powers of x on the top and the bottom are matched, right? So if I can somehow get rid of the y squared term here, then that'll allow me to cancel out the x squared on the top and the bottom, and then all that'll be left is just the y by itself, which is much simpler, right? So that's sort of the strategy that we're going for. So if we can get rid of the y squared, that'll simplify this expression. Okay, so now how to get rid of the y squared. So we have to do that by setting up some kind of inequality, right? Because the whole thing g of xy should satisfy some kind of inequality. So we have to set that up, right? So let's ignore the numerator for a second and just look at the denominator here, right? So we have the expression x squared plus y squared in the denominator. So I need to get rid of the x squared, right? So I need to get rid. I want to get rid of the y squared, right? So if I get rid of the y squared, what does it look like? Just the absolute value of x squared, right? So if I look at these two expressions and try to compare them, can I say anything about them at all? So here, I mean, they're almost the same, except the expression on the left is adding a y squared, right? So first of all, because y squared is being squared, y squared is always non-negative, right? So you're adding something non-negative to this thing here on the left side here, right? So when you're adding something non-negative, it typically has to make it at least bigger, right? So I can say that the expression on the left is always greater than or equal to the expression on the right. And again, the reason is because the plus y squared is always non-negative. Okay, so this is the inequality we're going to start out with, and we have to somehow use this inequality to say something about this expression here. So this x squared plus y squared is in the denominator, right? So let's take reciprocals. So if I take the reciprocal, the rule is that I have to flip the inequality. Okay, so we got this, and then now I need to turn this expression into this thing here, right? So what is the difference? Well, the denominator here is the same as the denominator here, so the only thing that's missing is the numerator. So I multiply both sides by the same numerator, and I'm allowed to do that because of the absolute value, everything is positive. So when I multiply both sides, it doesn't change the inequality. So I get the x squared y over x squared plus y squared is less than or equal to x squared y, right? So the same thing needs to be done to both sides. This is just x squared. This side only has the x squared on the bottom. Okay, so now I've finally gotten rid of the x squared, the y squared, and so this x squared and this x squared can cancel. All I'm left with is just the absolute value of y. And okay, so again, this let me make a notation here. So we're still following the outline for theorem 2.1, right? So this expression here was the f of x y minus L, right? So I mean, that's exactly what we wrote down here, right? So this expression was the f of x y minus L, and so we're using this inequality to compare it to this function, and so that's exactly my g of x y, right? So this exactly is my g of x y. Okay, so to complete the theorem, I have to calculate the limit for my simpler function g, and the limit should be equal to 0. And if that's the case, I can conclude that the original limit has the value of L that I stated here. Okay, so let's try to finish up. Right, so we're in step 4. Yeah, so that now we're finally in step 4. So I have to calculate the limit. So g only contains y, right? So it's the limit as y goes to 0 of the absolute value of y. Right, so again, I calculate the limit for g. But okay, so now y goes to 0. So just, plug in 0, you get 0. Right, so we see that this limit is equal to 0. So that's exactly what we want. And so now we can conclude limit exists and is equal to 0, because that was my L, and L is equal to 0. Okay, so finally we can say that the limit exists, and we've calculated the limit. So again, trying to apply this procedure for the squeeze theorem is not straightforward at all. So it takes a little bit of practice to get everything here set up properly.